Algebra by Michael Artin. Chapter 2, Groups. Section 5, Equivalence Relations and Partitions. Fundamental mathematical construction is to start with a set S and to form a new set by equating certain elements of S according to a given rule. For instance, we may divide the set of integers into two classes, the even integers and the odd integers. Or we may wish to view congruent triangles in the plane as equivalent geometric objects. This very general procedure arises in several ways, which we will discuss here. Let S be a set. By a partition P of S, we mean a subdivision of S into non-overlapping subsets. 5.1. S is equal to the union of disjoint non-empty subsets. For example, the set 1, 3, the set 2, 5, and the set 4 form a partition of the set 1, 2, 3, 4, 5. The two sets of even integers and odd integers form a partition of the set Z of all integers. An equivalence relation on S is a relation which holds between certain elements of S. We often write it as A equivalent to B and speak of it as an equivalence of A and B. 5.2. An equivalence relation is required to be 1. Transitive. If A is equivalent to B and B is equivalent to C, then A is equivalent to C. 2. Symmetric. If A is equivalent to B, then B is equivalent to A. 3. Reflexive. A is equivalent to A for all A member of S. Congruence of triangles is an example of an equivalence relation on the set S of triangles in the plane. Formally, a relation on a set S is the same thing as a subset R of the set S cross S of pairs of elements, namely the subset R consists of the pairs A, B such that A is equivalent to B. In terms of this subset, we can write the axioms for an equivalence relation as follows. 1. If A, B is a member of R and B, C is a member of R, then A, C is a member of R. 2. If A, B is a member of R, then B, A is a member of R. And 3. A, is a member of R for all A. The notions of a partition of S and an equivalence relation on S are logically equivalent, although in practice one is often presented with just one of these two. Given a partition P on S, we can define an equivalence relation R by the rule A is equivalent to B if A and B lie in the same subset of the partition. Axioms 5.2 are obviously satisfied. Conversely, given an equivalence relation R, we can define a partition this way. The subset containing A is the class of all elements B such that A is equivalent to B. This subset is called the equivalence class of A, and S is partitioned into equivalence classes. Let us check that the equivalence classes partition the set S. Call C sub A the equivalence class of an element A, a member of S. So C sub A consists of the elements B such that A is equivalent to B. 5.3. C sub A is equal to the set B, a member of S, such that A is equivalent to B. The reflexive axiom tells us that A is a member of C sub A. Therefore, the classes C sub A are not empty. And since A can be any element, the classes cover S. The remaining property of a partition, which must be verified, is that the equivalence classes do not overlap. It is easy to become confused here. Because A is equivalent to B, then by definition B is a member of C sub A. But B is a member of C sub B too. Doesn't this show that C sub A and C sub B overlap? We must remember that the symbol C sub A in our notation for a subset of S defined in a certain way. The partition consists of the subsets, not of the notations. It is true that C sub A and C sub B have the element B in common. That is all right because these are two notations for the same set. We will show the following. 5.4. Suppose that C sub A and C sub B have an element D in common. Then C sub A is equal to C sub B. Let us first show that if A is equivalent to B, then C sub A is equal to C sub B. To do so, let X be an arbitrary element of C sub B. Then B is equivalent to X. Since A is equivalent to B, transitivity shows that A is equivalent to X, hence that X is a member of C sub A. Therefore, C sub B is a subset of C sub A. The opposite inclusion follows from interchanging the rules of A and B. To prove 5.4, suppose that D is in C sub A and in C sub B, then A is equivalent to D and B is equivalent to D. Then, by what has been shown, C sub A is equal to C sub B is equal to C sub B as required. Suppose that an equivalence relation or a partition is given on a set S. Then we may construct a new set, S bar, whose elements are the equivalence classes or the subsets making up the partition. To simplify notation, the equivalence class of A or the subsets of the partition containing A is often denoted by A bar. Thus, A bar is an element of S bar. Notice that there is a natural surjective map, 5.5, mapping S to S bar, which sends A to A bar. In our original example of the partition of S equals Z, the set S bar contains the two elements, even and odd, where the symbol even represents the set of even integers and odd the set of odd integers, and 0 bar equals 2 bar equals 4 bar, and so on. So we can denote the set even by any one of these symbols. The map 5.6, mapping Z to the partition even, odd, is an obvious one. There are two ways to think of this construction. We can imagine putting the elements of S into separate piles, one for each subset of the partition, and then regarding the piles as elements of a new set S bar. The map S to S bar associates each element with its pile. Or we can think of changing what we mean by equality among elements of S, interpreting A equivalent to B to mean A is equal to B in S bar. With this way of looking at it, the elements in the two sets S and S bar correspond, but in S bar, more of them are equal to each other. It seems to me that this is the way we treat congruent triangles in school. The bar notation 5.5 is well suited to this intuitive picture. We can work with the same symbol as in S, but with bars over them to remind us of the new rule. 5.7. A bar equals B bar means A is equivalent to B. This notation is often very convenient. A disadvantage of the bar notation is that many symbols represent the same element of S bar. Sometimes this disadvantage can be overcome by choosing once and for all a particular element or a representative in each equivalence class. For example, it is customary to represent even by 0 bar and odd by 1 bar. 5.8. The partition even, odd is equal to the partition 0 bar, 1 bar. Though the pile picture is more immediate, the second way of viewing S bar is often the better one because operations on the piles are clumsy to visualize, whereas the bar notation is well suited to algebraic manipulation. Any map of sets phi mapping S to T defines an equivalence relation on the domain S, namely the relation given by the rule A is equivalent to B if phi of A is equal to phi of B. We will refer to this as the equivalence relation determined by the map. The corresponding partition is made up of the non-empty inverse images of the elements of T. By definition, the inverse image of an element T, a member of T, is the subset of S consisting of all elements S such that phi of S is equal to T. It is denoted symbolically as 5.9. Phi inverse of T is equal to the set S, a member of S, such that phi of S is equal to T. Thus, phi inverse of T is a subset of the domain S, determined by the element T, a member of T. This is symbolic notation. Please remember that phi inverse is usually not a function. The inverse images may also be called the fibers of the map phi. The fibers phi inverse of T, which are non-empty, which means T is in the image of phi, form a partition of S. Here the set S bar of equivalence classes, which is the set of non-empty fibers, has another incarnation as the image of phi of the map. Namely, there is a bijective map, 5.10, phi bar mapping S bar to the image of phi, the map which sends an element S bar of S bar to phi of S. We now go back to the group homomorphisms. Let phi mapping G to G prime be a homomorphism, and let us analyze the equivalence relation on G, which is associated to the map phi, or equivalently, the fibers of the homomorphism. This relation is usually denoted by congruence rather than by equivalence and is referred to as congruence. 5.11. A is congruent to B if phi of A is equal to phi of B. For example, let phi mapping C star to R star be the absolute value homomorphism, defined by phi of A is equal to the absolute value of A. The induced equivalence relation A congruent to B if the absolute value of A is equal to the absolute value of B. The fibers of this map are the concentric circles about O. They are in bijective correspondence with elements of the image of phi, the set of positive reals. 5.12 figure. Fibers of the absolute value map, C star to R star. The relation 5.11 can be rewritten in a number of ways, of which the following will be the most important for us. 5.13 proposition. Let phi mapping G to G prime be a group homomorphism with kernel n, and let A and B be elements of G. Then phi of A is equal to phi of B if and only if B is equal to AN for some element n a member of n, or equivalently if A inverse of B is a member of n. Proof. Suppose that phi of A is equal to phi of B. Then phi of A inverse times phi of B is equal to 1. And since phi is a homomorphism, we can use 4.1 and 4.3 to rewrite this equality as phi of A inverse B equal to 1. Now, by definition, the kernel n of the set of all elements x a member of G such that phi of x is equal to 1. Now, by definition, the kernel n is the set of all elements x a member of G such that phi of x is equal to 1. Thus, A inverse B is a member of n, or A inverse B equal n for some n a member of n. Hence, B equal AN as required. Conversely, if B is equal to AN and n a member of n, then phi of B is equal to phi of A times phi of n equal to phi of A times 1 equal phi of A. The set of elements of the form AN is denoted by AN is called a coset of n in G. 5.14. AN equal the set G a member of G such that G equal AN for some n a member of n. So the coset AN is the set of all group elements B which are congruent to A. The congruence relation A congruent to B partitions the group G into congruence classes, the cosets AN. They are the fibers of the map phi. In particular, the circles about the origin, depicted in 5.12, are cosets of the absolute value homomorphism. 5.15 figure, a schematic diagram of a group homomorphism. An important case to look at is when the kernel is the trivial subgroup. In that case, 5.13 reads as follows. 5.16 corollary. A group homomorphism phi mapping G to G prime is injective if and only if its kernel is the trivial subgroup 1. This gives us a way to verify that a homomorphism is an isomorphism. To do so, we check that the kernel of phi is equal to the set 1, so that phi is injective, and also that the image of phi is equal to G prime, that is, that phi is surjective. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall.
It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.